All right, welcome everybody. It's my pleasure to introduce, to those of you who don't already know her, Meredith MacGregor, who is here as a National Science Foundation Astronomy and Astrophysics postdoctoral fellow. She's been with us since last summer, be here for another 2 or 3 years, because we also gave her a Carnegie Fellowship. So we really wanted her to come, and we were glad when she decided to. Meredith got all of her education at Harvard University, so we're also introducing her to another aspect of the real world here. As academic institutions is about as far from the real world as it gets, but perhaps Harvard is second, I don't know. So she got her PhD there in 2017, working on ALMA Observations. So ALMA is you'll hear about, but it's the Atacama Large Millimeter Array, fantastic new National Science Foundation facility in the Southern Hemisphere, and she used that. She used the Very Large Array in New Mexico. She used the Submillimeter Array in Hawaii, all to do studies of disks around stars. Her advisor was Dave Wilner, some of you know. She's been the PI on, I think, 5 ALMA proposals, which is pretty spectacular for a young person in the field. You can also find her helping our astronomical community. She's been sitting on the Far Infrared Science Interest Group, working on the science case for the next large cold space telescope, which is currently being known as the Origin Space Telescope. She's an ambassador for the Worldwide Telescope. If you want to know about Worldwide Telescope, ask her that. But as you know, the National Science Foundation Fellows have responsibilities for education projects as part of their fellowships, and she's working with our First Light people at P Street to develop an astronomy curriculum. And last but not least, she will be the chair of the Gordon Research Seminar at the next Origins of Solar Systems meeting that Larry is the chair of. I am the co-chair of, so we have total Carnegie domination of that. But the research seminar is meant for grad students and postdocs to learn about the other aspects of the field that they are not experts in. So for astronomy for geochemists and geochemistry and cosmochemistry for astronomers. So I encourage you all to come to that, and you can ask Meredith about the research seminar. And with that, I will let her actually get on with her talk. So, well, go ahead, Meredith.
This works? Yes. Excellent, okay. No mic difficulties. Okay, thanks to Alicia for the lovely introduction. So today I want to talk to you about debris disks as probes of planetary system evolution. So I'm sure many people in the audience are not familiar with what a debris disk is, so we're going to start with some basics as what debris disks are and why they are exciting. So for people who attended Jehan's talk several weeks ago, you've already seen this image. This is the general picture of circumstellar disk evolution, so how we go and form stars and planets. So we start with a giant molecular cloud. We've put it times 0 here. We form stars, bits of this cloud collapse, and we form what we call a pre-main sequence star with a disk around it. And this is what's called a protoplanetary disk. So it's a gas-rich, dust-rich, actively accreting onto the star disk. And we think that during this kind of 1 to 10 million year lifetime of protoplanetary disks, we form planets. And then somehow, after about 10 million years, most of the material from the protoplanetary disk clears out. And what we're left with is our mature main sequence star, whatever planets managed to form during this phase, and the leftover material. And the leftover material is what we call a debris disk. So to draw the distinction between these two types of disks a little bit better, protoplanetary disks are around pre-main sequence stars. They're gas-rich. They have active accretion onto the star. You can see this picture of HH30 with these jets, this very flared, optically thick disk. And debris disks are now around main sequence stars. Traditionally, we've thought that they have no gas in them, but perhaps more accurately, they have very little gas. We'll talk a little bit more about that later. They no longer have accretion, and they're optically thin. So this is this lovely image of Fomalhaut, kind of one of the most famous debris disks. Looks a little bit like the Eye of Sauron from Paul Callis' paper in 2005. So I want to emphasize one point here in that the material in debris disks we think is second generation. So there are various processes in disks that remove dust, and they operate on much shorter timescales than tens to hundreds to billions of years, like we see debris disks at, which means that this material is getting actively stripped out. So something has to be reproducing it. And what we think is happening is that we have what are termed planetesimals, which are kind of akin to comets and asteroids in our own solar system that are colliding together and grinding down into smaller and smaller dust grains. So the material that we're seeing with our lovely HST and ALMA images is actually this second generation material that is sort of baby planets that didn't quite make it to the full planet stage. They're now grinding back down. So the very first debris disks were simply detected as what we call excess infrared emission, most notably by the IRAS satellite back in the 1980s. So what I'm showing here is what's called a spectral energy distribution, or SED, which is essentially just the flux of a star as a function of wavelength, with increasing wavelength going to the right. So the black here is what a model for a stellar photosphere, so a naked star. And then the data points here for this object are taken from longer wavelength facilities in the infrared. And you can see that as you go out to these longer wavelengths, the flux ticks up. So there's this extra bump in purple that's above what we would expect if it was a star. So this is interpreted as basically dust around the star that's absorbing the stellar starlight and re-radiating it as thermal emission or heat, which produces this kind of infrared and millimeter excess. Now, we've had tremendous advances in telescopes, and we can actually take these infrared excess sources and resolve them as these beautiful disk structures. So these are 4 images at different wavelengths of the same debris disk. This is AUMIC, which is one of only a few debris disks known around an M-dwarf type star. The top image is from SPHERE. This is in the near IR. You can see these beautiful waves actually moving outwards in the disk. Then we have Herschel at 70 microns, ALMA, the Atacama Large Millimeter Array, which you'll hear quite a bit about, at 1 millimeter, and the VLA all the way out at 1 centimeter wavelengths. So we can not only resolve structure in these disks, but we can resolve wavelength-dependent structure. We can see how the structure in the disk changes at different wavelengths of observations. Okay, so I just told you that we can observe debris disks at any wavelength we want. Why would we be particularly excited about the millimeter? And there's a few answers to this. We would really like to know where those planetesimals are that are colliding and grinding back down. And these planetesimals are large. They're kilometers in size, so we cannot observe them directly, but we want to probe them. So the millimeter grains are larger, and we think that they're gravitationally bound to where these parent planetesimals are. Smaller grains, so micron-sized grains that we see with like the Hubble Space Telescope, are easily blown out by winds from the star or stellar radiation, so they're less reliable tracers. So if we really want to know the structure of the underlying belt, which is possibly being shaped by planets in the system, the millimeter is kind of our best probe. And interferometry at millimeter wavelengths gives us the high resolution we need in order to actually resolve that detailed structure and model it. So Alicia already mentioned all these telescopes. There's an array of millimeter and centimeter telescopes that we can use to do this. And most of the data that I'm showing in this talk comes from ALMA, which is this brand new telescope completed only a few years ago in the Atacama Desert in Chile. So the Atacama Large Millimeter Submillimeter Array. And I just wanted to take one slide to introduce you to what exactly it is, since not everybody uses ALMA on a daily basis. So ALMA actually consists of really 2 arrays of telescopes, and I'm going to talk about both of them. The first is what we call the main array. So there are 50 dishes that are all 12 meters in diameter. And then there's a complementary array called the Atacama Compact Array, or ACA for short, which is 12 7 meters, so slightly smaller antennas. So the main array can be spread out to very long baselines. These can be spread out to 16 kilometers apart. The DC-centric view is if you put ALMA in its most compact configuration, it would fit entirely on the White House ellipse. If you put it in its most extended configuration, it would span the entire beltway. So it's reconfigurable and a kind of really impressive feat of engineering to build this telescope. The compact array is always in a compact configuration. So it's mostly used for unresolved sources or sources that are very extended on the sky. And pretty much all the observations that I'm going to talk about today are taken at 1.3 millimeters in wavelength. So this is a frequency of 230 gigahertz, or what we call band 6 with ALMA. And with radio telescopes, you actually observe not at one single wavelength, but at a range of wavelengths, what we call a bandwidth. So that's 8 gigahertz for ALMA, and we can actually observe in 2 different linear polarizations. So this can give us some information about emission mechanisms from different sources. Okay, so I've organized the bulk of my talk into sort of 2 outstanding questions in debris disks and planetary science that we would like to answer and have kind of different and complementary observational approaches. So the first is, what constraints can we place on the material properties of actual grains, the dust in these debris disks, and what can that tell us about planet formation and planet composition? And to do this, I've been using a strategy where we take the VLA and ATCA, which operate at centimeter wavelengths, so much longer wavelengths, and actually measure this spectral index, so how the flux of the source varies as a function of wavelength, in order to probe the grain size distribution in these disks. And doing this, we've been able to place the first observational constraints on what the actual grain size distribution is in debris disks. The second question is, we see all these asymmetric structures in debris disks. Are they produced by planets? And if that's the case, can we actually probe for additional wider separation Neptune analog planets in these systems by studying the structure of debris disks? And to do this, we actually go and resolve with high resolution the structure of individual debris disks with ALMA, and then try and model that. And so I'm going to show you some new ALMA images of some nearby debris disks, most notably the Fomalhaut, and then these two HD numbers, HD32297 and HD61005 debris disks that have kind of unique structures that we have been trying to resolve. Okay, so starting with grain properties in debris disks. Why is this interesting? Debris disks are really, as I said, produced through the collisions between these planetesimals. So these are the building blocks of planets that we're now grinding back down. And we would like to know what the planetary compositions is, and perhaps a way to get at this is by studying the compositions of this leftover stuff. So we want to know the composition, the size distribution, the porosity. We can model this from observations, but a lot of these are degenerate with each other. So by trying to place constraints on one thing, the size distribution, hopefully we can get at the rest of this information. So the key thing to remember here is that by looking at different wavelengths, we are looking at different size dust grains. So this is a plot of the emissivity, so how efficiently a grain emits as a function of wavelength for different size grains, from small in purple to green for larger grains. And if you pick any given wavelength, the large grains, grains that have a size comparable to the wavelength, are the most efficient emitters. So we can sort of sum that up in saying the observing wavelength that we're looking at is equivalent to the grain size, roughly speaking. Now this plot here is showing the number of grains as a function of grain size. And we typically assume that the number of grains as a function of size goes as some power law, where A is the grain size to some index Q. This shows us a few things. One, there are many, many more small grains in disks. And second, the flux density as a function of wavelength is directly related then to the grain size distribution. So by measuring the flux density at different wavelengths, we are probing the amount of material of that different size. So this means that if we want to learn about the grain size distribution and we want to probe these kind of larger centimeter-sized grains to do that, we need to look at centimeter wavelengths. This has actually really only been possible in the last 5 to 10 years because of some significant advances in these, the VLA and ATCA. They expanded the bandwidth of the telescope, which gave us the sensitivity to actually detect debris disks at these wavelengths. So this is the equation that shows us how that Q, that power law index, the grain size distribution as a function of grain size, varies according to alpha millimeter, which is the spectral index that we're measuring, so the function, how the flux depends on the wavelength, and a few constants, where alpha Planck here is the spectral index of the Planck function, and since we're at long wavelengths, we assume we're in a Rayleigh-Jeans distribution, so this is about 2. And beta S is an opacity parameter, which has been measured for interstellar grains to be about 1.8. So we can treat these as approximately constants and directly relate what we measure from the flux distribution back to the grain size distribution. So what do we even expect that to be? There's been a wide range of theoretical work on grain size distributions in disks. The most classical paper is from 1969 by Doniani, which makes the simplest assumption that all collisions in the disk are independent of the strength of the bodies and the velocity of the bodies. So maybe that's not the most reasonable thing. We might expect that different size grains are moving at different rates. But if you work this out, you can predict that that grain size distribution is about 3.5. So let's imagine that we then incorporate a size-dependent velocity distribution. So we relax one of those assumptions. This has been worked out, and that predicts steeper grain size distributions, so somewhere on the order of 3.6 to 4. And we can work out the other opposite case in which now we have bodies of different strengths. So we can imagine that instead of having hard rocks colliding, we might have fluffy ice balls. And in that case, then the grain size distribution flattens. So Q is somewhere between 3 and 3.25. So this is a pretty wide range, spanning all the way between 3 and 4. So we don't really have a good constraint on this. So what we set out to do was actually to do the first kind of survey of grain size distributions in disks. We selected a sample to observe with the VLA based upon having accessible declinations. They could actually be observed by the telescope, having strong millimeter emissions, so we knew that we could actually detect them, and a small angular extent, so we would get a total flux measurement instead of resolving out the source. These are the targets, and then we complemented these 7 targets by 8 more targets observed with ATCA. So ATCA is the Australia Telescope Compact Array down in Narrabri, Australia. This is kind of the slideshow of images. Of the VLA disks, we detected 6. One of them was undetected. Most of these are kind of unexciting blobs. The one thing I wanted to draw your attention to is AUMIC, which I've already mentioned. The star, as it turns out, is doing funny things at centimeter wavelengths. So the black is the disk emission, and the white contours are actually the star. So the star flared during our observations. So in order to place any constraints on the disk flux, we had to subtract out a time-dependent model of the star. So inevitably, all the numbers for AUMIC are lower limits, because by subtracting out some of the star, we subtracted away some of the disk flux. And then these are the ATCA sources. We detected 6 of the 8 sources with ATCA. Okay, so the results from this are summed up in this one plot. This is now showing each individual source that we looked at, all 15, ordered by stellar luminosity. So the brightest A-type stars are at the top, and the less luminous M-type stars, AUMIC, are at the bottom. And then plotting for each source the Q value. So this is that grain size distribution power law index. The weighted mean is 3.36 plus or minus 0.02, which is shown by the black line here, and with a full range that spans between 2.84 and 3.64. So you'll note that there's one very clear outlier here. HD 141569 has a lot of interesting things going on with it. It's a much younger source, so it might not be a true debris disk. And in fact, some follow-up observations that we have been doing show that the star is actually also doing something funny. So if we ignore this source and we look at just the rest of the sample, they're all pretty tightly clustered around the mean. We do note that there is a kind of tentative trend with spectral type, where these sort of brighter A-type stars have steeper grain size distributions than the sort of later K and M-type stars. This is kind of tentative largely because of small number statistics. There are only a handful of debris disks known around K and M-type stars, so we only have measurements for a very few handful of sources. Similar results have been seen doing a kind of similar approach, but at infrared wavelengths. So instead of looking in the millimeter, looking in the infrared, and they have noted a similar trend. So this could tell us something about how efficient the kind of earlier stage protoplanetary disks are at forming planets that might stir the disk. But more work needs to be done to actually kind of firm this up. Yeah?
Could you say more about this beta parameter? Because you said it was based on dust properties.
Yes. Yes. Yeah, so beta is a significant uncertainty. It doesn't change the distribution of the sources because it's just a constant that we use to divide out. So well, there would be no reason to expect that beta would be different that I can think of between A and M-type stars. I would acknowledge that beta could be different between interstellar dust and like debris disk processed dust. But I don't know if there's a reason that it would be different between the different types of stars. Yeah, yeah. So that number is from Bruce Strain's 2006 paper. It is what people have traditionally used to assume. There's been a number of papers that have tried to measure vapor, and they generally say it's somewhere between 1.5 and 2. So the range is not large. But okay. So the hashed regions on this plot show us the models that I talked about before. So how do our results compare to kind of the range of models that we see? They're, interestingly enough, most consistent with the Doniani results from 1969 with this very simple model. They're also consistent with some numerical models of individual disks. This yellow region is for AUMIC. They're not at all consistent with these very steep models from the Pan and Schlichting paper that incorporate this size-dependent velocity distribution. And a bunch of them are fairly consistent with these shallower values. So this could imply that maybe the grains in debris disks are fluffier. They're kind of porous, more porous than rocky. There have been some papers that have tried to actually measure the porosity of grains from scattered light observations. So there's a work from James Graham in 2007 where they actually try and do this for AUMIC, and they get the dust grains are something like 90 to 95% porous, but there's pretty few observational constraints. But for the first time, we were actually starting to really place some real constraints on this kind of wealth of modeling work to say something really about what the size distribution is like in these disks. Okay. So I'm going to transition into the other question, which is resolving this debris disk structure. So to kind of motivate this again, why would we be excited to resolve debris disk structure? We think that these are systems which have planets in them. And if there's a planet orbiting inside of a dust disk, you might expect the planet to shape the disk. So you could imagine having sort of a wealth of different structures resulting from this gravitational interaction, some warps or clumps, asymmetries or eccentricities in the disk, sharp edges where material gets carved out. And we see evidence in other systems for this. So this is HD 15115. This disk has this dramatic asymmetry. One side of the disk is in the Hubble image, twice as extended as the other side. Beta Pic actually has a warp in the inner part of the disk, which can be explained by the then later detected planet, Beta Pictoris b. And even our own Kuiper belt, if you look at the classical Kuiper belt, is confined. It's between about 40 and 48 AU with fairly sharp edges. So this might be a way to probe for other wide separation planets, say Neptune analogs, that we cannot currently detect via radial velocity or transit techniques that require upon observing multiple orbits of a system to confirm. And if we could detect such structures in external debris disks, we could actually model them and infer the presence of giant planets. Okay. So I like to show this flash. This is kind of the suite of debris disks imaged before ALMA. So all of these images are taken in the kind of infrared and submillimeter wavelengths. There's some structure. Most of them look like blobs. And then this is the suite of the exact same disks now with ALMA. So ALMA has really revolutionized our ability to actually do this. So you can see things that go from being blobs to being these beautiful narrow rings. There's some interesting structure. So we can now actually resolve these disks well enough to begin to really model them and try and piece this together. So I wanted to highlight 3 different systems. This is Fomalhaut, and then HD 6105 and 3297, which I've been working on with Alicia for the last kind of 6 months or so. So let's start with these 2 disks. These disks are really distinctive in that if you look at their Hubble Space Telescope scattered light images, they have these massive wings. So you can see this extended emission that's kind of flaring outwards from the kind of major axis of the disk. So they're both edge-on. We're assuming that the disk is kind of oriented like this, and now they have these kind of massive wings flaring out. One of them is an A-type star. It's at 136 parsecs, somewhere around 30 million years old. The other is a G-type star, 37 parsecs at 40 million years old. And the question has always been, what's producing these swept-back wings? You can imagine one of the popular ideas has been that these disks are actually moving into a dense clump of the interstellar medium, so they're hitting this clump of ISM gas that's dense, and it's sort of stripping out these grains into this halo. So you imagine kind of a ram pressure stripping scenario, removing grains from the disks. So we went out to try and actually look at this with ALMA. So these are now the new ALMA images overlaid on the HST images. So these are contours of 4 times the RMS noise in the image. And to guide your eye a little bit, I've put on some arrows. So what's really noticeable about these is that we actually detect hints of this extended emission in the millimeter observations, which we have not seen before. So this is not as well resolved, but you can see these 2 bumps are what we call onsci, so they're limb brightening, essentially. We assume these disks are optically thin and they're edge-on, so we see more material at the edges of the disk. But then there's this kind of extra fluff. And you can see it particularly well. There's these little fingers that extend out along these scattered light wings. So this is the first time we've ever seen extended emission like this at longer wavelengths. And we can then model this. So I've developed a modeling code which actually fits directly to the millimeter visibilities. So instead of fitting to the image, which is now the Fourier transform of our visibilities, we can avoid a lot of nonlinearity by fitting directly to the raw data from the telescope. And it allows us to actually constrain the errors on the parameters. So we define a model that is axisymmetric, so it's radially symmetric, but has a surface brightness profile which is a radial surface brightness profile, defined as some power law. So this incorporates temperature and surface density. The temperature we assume just falls off as r to the minus 0.5. This is kind of a classical temperature fall-off profile. And in this case, we have a broken power law for the surface density, which is shown here. So as you move away from the star, the surface density actually increases from the inner edge of the disk to what we're calling the halo radius. So this is where that extended emission starts, and then decreases out to some outer radius. So this is kind of a schematic of the model. You can see that the flux sort of increases and then kind of tails out slowly. And then we normalize the flux of the belt, and we can also fit for the geometry of the disk, the inclination, the position angle, its orientation on the sky relative to us. And when we do that, this is what we get. This is showing on the top 32297, on the bottom 61005. This is the data again. Then the model at kind of full resolution. The model convolved with the beam of the telescope, so comparable to the data. And then the residual is what we get by subtracting the model from the data. So this two-component model fits fairly well. The residuals are small, although present. So both disks are well described by a model that has both kind of a classical planetesimal belt with a rising surface density gradient and then this extended outer halo. Okay, so to dig into that a little bit more, 32297, the actual fit has a belt at 110 AU that has a width of 53. We like to quote a parameter in debris disks called the fractional width. So this is just the width of the disk over the radius. In this case, it's fairly broad. It's 0.48. And to put that into context, the classical Kuiper belt has a fractional width of 0.18. And the Fomalhaut debris disk, that beautiful ring I've shown a few times, has a fractional width of 0.1. So this is fairly broad in comparison. The halo, that extended emission, this fluff, extends all the way out to 340 AU from the star. And we see this rising surface density gradient, which I've said a couple times, that's sort of counterintuitive. We wouldn't really expect the surface density of material in a disk to increase as you get further and further away from the star. Classically, you would assume it just sort of falls off. You have more material close to the star, and then it falls away. So there's some models that predict this result, which imply that you can actually have ongoing planet formation on the inner edge of debris disks. So you're starting to build things back up into sort of Pluto-sized bodies. And by doing that, you effectively collisionally deplete away small grains. But the timescales are too long on the outer edge of the disk, so you haven't started rebuilding material on the outer edges. So you kind of deplete on the inner part, and then don't deplete on the outer part, so you produce what looks like a rising surface density gradient. And we start seeing this in a number of debris disks. There's kind of a sample of 6 or so disks now where we see these rising surface density gradients. In 32297, we detect 12CO gas, which I'm going to go into in the next slide. And we see this potentially asymmetric structure at about a 3 to 4 sigma level, conveniently on the side of the disk where those extended wings are. For 61005, the belt is closer in. It's at 64 AU with a width of 27, which is similarly broad. So the fractional width is 0.42. The halo extends out to 160 AU. And again, it's best fit by this rising surface density gradient. We don't detect any gas in the system. And there are also residuals, which in this case are sort of concentrated towards the star. So this could be evidence that there's actually an additional sort of warm asteroid belt analog in the system that we're not resolving in the current observations. Okay, so to tie this back to the initial question I asked, which is what is producing these wings? We have never seen wings in the millimeter before. And if we remember all the way back when I said that by observing different wavelengths, we observe different grain sizes, this means that now we're observing millimeter emissions, so there must be large grains. We could actually do a toy calculation of how many small grains we would need in that outer halo to account for the flux. If we do that, then the fractional mass we get for that halo of small grains compared to the width is somewhere between 50 and 80%. So that's a huge mass of small grains that we would need in order to account for that. So the most logical explanation is that we actually have larger grains populating these extended halos. So these are kind of the 3 theories that people have put forth to explain these structures. The first I already mentioned, which is interactions with the interstellar medium. So having these disks colliding with dense interstellar gas and stripping away grains. This works really well for tiny grains. It does not work so well for large grains. It's very hard to actually strip out a millimeter or centimeter sized grain from your disk. You could also imagine having interactions with the disk itself. You could have some sort of massive collision that occurs. That's a transient type event, so you collide several large comets and release a whole bunch of material. Typically, you would expect that to be asymmetric. It also generally involves smaller grains and not large millimeter grains. And then the final thing is that we could have interactions with planets. So you could place a planet on sort of an eccentric orbit inside of the disk, and as it perturbs the grains, it incites collisions and can produce wing-like structures this way. So there's a number of theoretical models that work this out. If we come to the conclusion that there are likely millimeter grains in these halos, then this is really sort of the favored scenario, because these both don't work very well for the larger grains. So this is kind of exciting in that this is the first time we've seen evidence for this, and it points us kind of in the direction of possibly a planetary origin for these structures. Now, I just wanted to talk briefly about the gas detection in 32297. We always classically assumed that all of the gas in debris disks was removed so that we didn't expect to see any at all. And now with ALMA, we're starting to detect actually quite a bit of CO gas in a number of debris disk systems. So this is showing the moment maps. So this is basically the rotation of the disk. And then these are the individual channels. We detect, this may seem like a very small number, but for a debris disk, this is actually quite large, about 4 times 10 to the minus 4 Earth masses of CO. There are a few interesting things about it, which we actually do not have an answer for, really, at this point. So this is showing on the left an overlay of the CO in the black and the dust, that dust continuum map in the colored orange contours. And they're pretty co-located. So it looks like the gas and the dust are originating from the same place in the disk. This tells us something about the origin, possibly, because the question has always been, we have this huge amount of gas. Where does it come from? Does it stick around from a primordial phase, so it's somehow lasting from the protoplanetary disk phase for tens of million years, and we're seeing it now, which is unlikely? Or is it produced through collisions of comets? So if these bodies in debris disks are actually really like comets and they're colliding, not only are they going to produce a collisional cascade of dust, but they might outgas CO. So if we see the dust and the gas in the same location, spatially located, that sort of makes that scenario more likely because we're seeing the dust and the gas in the same place, so these collisions are producing this gas. What's sort of odd is that the gas that we see in this disk seems to be sub-Keplerian. So we typically assume that things in a disk are moving in Keplerian rotation. We can work that out nicely, and we can make predictions for that. So this is showing the velocity now of the material, the gas in the disk, as a function of its radial offset, so offset along the disk major axis. And the black lines are what we would predict if everything was moving nicely Keplerian. The peaks in this plot are not there. So it seems like the gas is moving a few kilometers per second slower than we would predict if it's just orbiting like a Keplerian body. This has been seen for another debris disk that has a large amount of gas, also around kind of a late A star, Beta Pictoris. And it's been proposed that maybe there's some kind of radiation pressure that's actually slowing the gas down. But this is kind of a new and interesting result that requires some more investigation to figure out what exactly is the explanation for that.
Because if the dust is going in and it's generating the CO, then you might explain
Yeah, I mean, it is possible that there is pointing Robinson drag. It is an A star. I have not worked out the numbers. There's been kind of various opinions on whether that's a significant effect in these systems or not, but it is an idea. Okay. So then I want to transition to my other favorite disk, which is Fomalhaut, the Eye of Sauron again. So Fomalhaut has been this object of much observational work because it's one of the closest debris disks. It's at 7.7 parsecs around an A-type star, and it's fairly old. It's about 440 million years old. And it's this beautiful narrow ring. There was a detection of a possible planet in the system, Fomalhaut B, although follow-up observations show that the orbit of Fomalhaut B is actually crossing the disk, so this gray line is its tentative orbit. So that makes it maybe less likely to be a planet. It's certainly not the planet that's shaping this disk. And it's been proposed that maybe it's just like a clump of dust. So there was a massive collision that's now orbiting. So there's been a lot of work with Hubble. And then it was imaged very early on by ALMA in cycle 0 by Aaron Boley. The tricky thing with Fomalhaut is it's so nearby that it's massive on the sky. So you cannot actually image it with a single pointing with ALMA. So they chose one pointing focused on this side of the disk and got half the disk. Then it was imaged again in cycle 2 with ALMA. So this now, the pointing's on the star, so it's getting kind of the minor axis of the disk, but missing the two on side, the major axis. So we actually designed a mosaic image. So this means taking multiple images of the source and then stitching them together, essentially. So we had 7 pointings, 1 on the star, 2 on either of the minor axis sides of the disk, and then 1 on each of the on-side to produce a complete map of the entire system. So this is the resulting image, which is now much lovelier. So you can actually see the entire disk with uniform brightness across the entire thing and then model it. So the modeling is a little bit different in this case because the Fomalhaut debris disk is very clearly eccentric. So the star is not actually at the centroid of the disk. And so we actually develop a new modeling code which computes the orbital parameters, the orbital positions for, say, about 10 to the 4 particles, test particles in a disk, and then creates a 2D histogram of all those particle positions and bins them into the desired pixel resolution that we want. And then we assume this r to the minus 0.5 temperature profile and compute the flux in each pixel now. And then we can account for the geometry of the disk, so the inclination and the position angle, so its position on the sky. And then we incorporate this all back into the same Monte Carlo Markov chain that we had been using previously. So this is the data model residual figure again. So the data, the model at full resolution, the model imaged like the data, and then the residuals, which in this case are very clean. We actually don't really detect any significant residuals except for this little blob, which people always ask me about. This is a submillimeter background galaxy. So submillimeter galaxies, distance high redshift galaxies, emit helpfully in the millimeter wavelengths, and ALMA is so sensitive that you actually expect to detect a fair amount of them in your images. So this is a helpful galaxy sitting in the image. So these are kind of the wealth of parameters that we can then fit for. So we fit for a flux of the belt, the flux of the central star that we detect, the radius, the width, the range of semi-major axes, inclination, position angle. There's 2 eccentricities. EF is a forced eccentricity. So this is actually the eccentricity of the planet that is forcing the bulk of the disk to have an eccentricity. And then there's an EP, which is the proper or intrinsic eccentricity, which is this kind of scatter in the eccentricity. So how much extra eccentricity all of the particles in the disk have on top of sort of their forced eccentricity. And then the argument of pericenter. The kind of most exciting thing to come out of this was that we, for the first time, detected what we've called Apocenter Glow, which was a theoretical prediction by Margaret Pan in 2016. So this is showing the Herschel, so infrared 70 micron image, in which the disk is actually noticeably brighter at pericenter, so the side of the disk closest to the star. And in our ALMA image, the disk is actually brighter at apocenter, the side of the disk farthest from the star. You can see this better in these brightness cuts. So this is showing cuts from the star to the pericenter side in purple, and then to the apocenter side in blue. So you can see not only that the star is visibly off-cent from the center, but also the difference of about 5 sigma between the apocenter and pericenter sides of the disk. And the explanation for this is that at shorter infrared wavelengths, you're more sensitive to the temperature of dust grains in the disk. So grains at pericenter are closest to the star, so they are heated up more, so they glow more brightly, so we see what's called pericenter glow in our shorter wavelength images. As we move to the millimeter, we become more optically thin. So we're actually more sensitive to the surface density of material in the disk rather than the temperature. And if you work out in a Keplerian orbit, for things that are orbiting in eccentric orbits, they actually spend more time at apocenter. So you predict that there should be a surface density enhancement at the apocenter point in the disk. So this is the first time we've actually seen this observationally, seeing pericenter glow at shorter wavelengths and apocenter glow at longer wavelengths. We also coincidentally detected gas, CO emission. In this case, we had to spatially average over the entire disk to make the detection, so we don't have a lovely rotation map, but we do detect somewhere between 0.65 and 42 now times 10 to the minus 7 Earth masses of gas. So this, if you remember back to 3297, is a factor of 10 to the 3 less gas. So this is a very, very small amount of gas, but CO gas nonetheless. Okay. Now, the exciting thing is that Fomalhaut is sort of the ideal test case to really look at the dynamics of planets and disks interacting, because the disk is clearly eccentric, so something has to be shaping it, and the question is what is doing that? And since we are able to actually fit for both the proper and the forced eccentricity, we can kind of try and probe this in this particular system. Depending upon whether a planet is shaping the disk or something else is shaping the disk, you actually expect there to be a azimuthal variation in the width of the disk as you go around the ring, with the maximum difference happening between the apocenter and the pericenter sides of the disk. So if there is really a planet that is shaping the disk, then we would expect most of the particles in the disk to be what we call apsidally aligned. So they have very little extra scatter in their eccentricity around the ring. And in this case, you can actually work out that for this small proper eccentricity case, the predicted width ratio is 1 minus the forced eccentricity to 1 plus the forced eccentricity. So this is a nice kind of theoretical prediction. For Fomalhaut, the forced eccentricity is 0.12. So this predicts that between pericenter and apocenter, the ring should actually be 4 AU thinner at apocenter than at pericenter. So that's a nice kind of testable prediction. If the proper eccentricity is large, so these grains are not apsidally aligned, then something else is going on, because it's very difficult to have a planet actually sculpting something with a high proper eccentricity. And there are examples of this. The epsilon ring of Uranus has a width at pericenter of 20 kilometers and 96 kilometers at apocenter. So this gives you a width ratio of 1 to 5. So if you were to observe a more extreme width ratio, you would kind of have a mark against this being a disk shaped by a planet. And nicely, ALMA actually has the resolution to do this. So these are simulated observations. I have a program that was accepted in the last ALMA cycle to actually do this, showing an observation at apocenter, so the far side of the disk, and pericenter, and then a cut across the width of each disk, so you can actually see the apocenter versus pericenter width difference of 4 AU nicely resolved. So with these observations, we should, for the first time, actually be able to robustly determine whether the disk is shaped by some perturbations from a planet. And in addition, we can look for any kind of additional substructure in the disk that might tell us something about the planet in the system. So hopefully we'll have results from this whenever ALMA actually takes the observations, and this will be kind of a fun, exciting project. Okay, so I wanted to end with a small segue into stars. Because if you've noticed, a lot of the images I've shown you have a lovely bright point source in the middle of them, which is the star. And as it turns out, we know very little about stars at millimeter wavelengths. They are doing very strange things, and we don't understand it. There's surprisingly little work done actually studying the dynamics of stars in this particular wavelength range. So I wanted to highlight something Alicia and I did, came out in February, on Proxima Centauri. So Proxima Centauri, for those who are not familiar, is the closest star to us with a potentially habitable planet. It's an M5.5, so it's an M-dwarf star, only at 1.3 parsecs. And the planet is at 0.05 AU, which puts it in the kind of temperature range to have potentially liquid water on its surface. There was a paper that came out at the end of last year that used all the observations to claim that in addition to having this planet, there was now a multiple ring system and a potential protoplanet in the system, which makes it kind of more akin to our own solar system to have these multiple dust belts and multiple planets. So what we did was to actually take these ALMA observations and reanalyze them to kind of dig into these dust rings a little bit more. So brief summary of the observations. They are taken in these 2 different ALMA arrays. So one's with the full array. There were 2 observations taken on the 25th of April in 2017. And with the ACA, it was observed 13 times, spanning between January 21st and March 24th of 2017. Okay. This is kind of, again, the summary. There are about 41 antennas there and 8 antennas in the ACA. And what do we look at? So this is the images showing the 12-meter Array images. On the left is both of those observations averaged together into one image. So we see a lovely point source, has a flux of about 101 microjanskis. These two panels are each of the individual observations, separate. So the point source is fairly consistent between them. And this one has a flux of 110, and then the last one has a flux of 94. For reference, the expected photospheric flux, so what we think that the photosphere, the star by itself, should be is 74 microjanskis. And then we can split this data up even more finely. So instead of now looking at kind of the average total hour and a half of observations averaged together, we can look at it in the individual integrations of the telescope, which are much shorter. So this is now showing each of these kind of 6-minute observations of the telescope for the first observation in blue and the second observation in red. And the gray region is the average. The flux is fairly consistent between them, but it is slightly above what we'd expect from just a photosphere by itself. So the original paper interpreted this as dust. So there's this slight excess of about 30 microjanskis. This could be from dust around the star close in an asteroid belt getting heated up and emitting at millimeter wavelengths. We actually think that that's not the case, and that instead we draw a comparison to AUMIC. So AUMIC, we have on the top here the VLA observations from actually the work I did trying to measure the size distribution. And we observed it 3 times. And the flux is varying all over the place in those observations. It flares. These two are taken about a day apart. This is about a month later. So it's jumping by orders of magnitude throughout all the observations. We also imaged AUMIC with ALMA. We got the beautiful edge on disk here and this bright point source in the center. And the bright point source was about 6 times brighter at millimeter wavelengths than we'd expect from just the stellar photosphere. So initially, we thought that this might be evidence for a hot asteroid belt. But you can actually construct a model of coronal heating in which essentially you have kind of continual breaking of the magnetic field lines in the stellar atmosphere that reconnect and release sort of a lot of small flares. And by doing that, you can produce a model that explains not only this emission we see in the millimeter, but the excesses and variation we see in the radio, and also the excesses and flares they see in the X-ray. So you can explain all of this sort of excess emission at a range of wavelengths just by a simple model of continual small flares in the star. Now, if we look at the ACA observations, this is kind of where it gets even more interesting. The left panel, again, is all of those 13 observations averaged together. The middle panel is the first 12 observations averaged together. So this is observations 1 through 12. And then the last panel is the final observation taken on March 24th. So you'll note there's a point source here, has a flux of about 340 microjanskis. In this middle panel, we actually don't detect anything above 2 sigma. There is nothing detected. So we can place an upper limit of 3 sigma upper limit of less than 200 microjanskis. And in the final panel, in this last observation, we have a flux of 1.17 millijanskis. So we can dig into this observation even more and go and look at the individual integrations from the telescope. So now taking this hour-and-a-half of observation and looking at it in 2-second bins, and this is what we actually see. So for most of the observation, there is nothing detected. And then we see this massive flaring event. So there's actually over 2 minutes, the star has a kind of brief, small pre-flare, and then a massive flare, and then tails away. The entire event lasts less than 2 minutes, and it brightens by a factor of 1,000 to a peak flux of about 100 millijanskis. So we can look at this in slightly more detail. On the top here, again, I'm showing the flux density as a function of time relative to the peak of the flare, but now binned more coarsely, so we get higher signal to noise. So we can see the flare. But we can also look at both the spectral index in the middle here and the polarization fraction. So I mentioned that these ALMA observations have 8 gigahertz of bandwidth to them, so we can calculate a spectral index over that bandwidth. And you can see as you go into the flare, it goes from being about 2, which is consistent with Rayleigh-Jeans emission, to dipping down to minus 1.7, minus 1.8, and then recovering as you come out of the flare. And the polarization fraction, so this is a lower limit on the linear polarization fraction, goes from being 0 to negative to 0.19 at the peak of the flare, and then recovering back to 0 as it leaves. OK, so what does this tell us? The the kind of most exciting thing is that we really don't know anything about the flaring properties of M dwarfs at millimeter wavelengths. This is the first time we've ever detected a flare from an M dwarf at these wavelengths at all. We have seen M dwarfs flare at other wavelengths, notably in the X-ray and the optical, and some at very long wavelength radio, but never in this kind of millimeter regime. We have seen millimeter emission from other types of stars and from our own sun. These are 4 detected solar flares in the millimeter. These are kind of the only 4 detected solar flares in the millimeter. And in the colors are the longer wavelength observations, and then the black and the gray are sort of higher energy X-ray. You can see kind of a range of properties here. In some cases, the millimeter and the X-rays are correlated. In some cases, they don't appear to be at all. The general properties of the solar millimeter flares, they have a flux of 7 times 10 to the 8 Janskis, which is a luminosity of 2 times 10 to the 13. In comparison, we have a luminosity of 2 times 10 to the 14. So the Proxima Centauri flare is still 10 times brighter than the brightest solar flares we've seen. And it has a very different spectral index. So we get a spectral index of minus 1.77. The solar flares actually have positive spectral indices, so somewhere between 0.3 and 5. So there's a lot more work to be done to understand the physics of millimeter flares, which is just kind of an unexplored area of stellar physics. In terms of the dust belts, what does this mean? Well, essentially it means that we can rule out all of the dust emission in this system. So this is kind of the schematic they had of the star and the known planet Proxima b, and then these multiple dust rings. So these 2 inner rings, there's no evidence for them because we can account for all the flux that we see simply from the star. The outer belt is a little bit tricky. So this is showing now, again, the image of all of the ACA data combined together, and then the outer belt they interpreted by kind of connecting these 5 blobs and sort of radially averaging, which gives you a belt that has a flux of about 1.7 millijanskis. So obviously the star flaring does not immediately impact these blobs, but there are a few caveats that are important to point out. One is background galaxies. So we see a background galaxy in the Fomalhaut image. There's been a number of papers that have actually simply tried to do the background source counts from all the observations, like how many background sources do we expect? And if you calculate that for this size image, you actually expect to have 13 plus 10 minus 8, so around 13 background galaxies in this image. So it'd be very easy to have 5 background galaxies within the image of these fluxes. In addition, Proxima is actually very close to the galactic plane, and it's in a region that is known to have high background cirrus emission, which confused some Spitzer observations taken in 2007 at 60 microns. In fact, they were unable to place any constraints on disk emission from the source simply because of the level of confusion. The current observations cannot rule out the presence of this outer belt, but there are some kind of strong caveats to keep in mind. And I think the real take-home from this is that if we want to understand and look for potential unresolved asteroid belts, which would be very exciting, right? We have an asteroid belt and a Kuiper belt in our own solar system, but so far we have yet to resolve an asteroid belt. We've resolved a lot of Kuiper belts, but no asteroid belts. We need to be cautious in understanding what the star is doing, because it's difficult to interpret unresolved excesses as due to dust if you don't actually know what the star is doing at the wavelengths that you're looking at. So that's my cautionary tale about millimeter stellar emission. And I just wanted to end by saying I think kind of we're really moving in a direction where we can, start piecing together the different parts of planetary systems and look not only at its disks and planets individually, but at how kind of the whole planetary system is together. And then I'll come back to, on my conclusion slide, the 2 questions that I asked previously and kind of what we have done so far to answer those. So what kind of constraints can we place on the material properties of grains and planetesimals and debris disks? We've placed the first observational constraints on the grain size distribution. We find this mean power law index of 3.36, and we see a tentative trend in grain size distribution as a function of stellar type. And in looking at these connection between disks and planets, we're able to model and characterize the resolved millimeter structure of a number of nearby debris disks now. We can start to connect that structure to planetary systems. We're starting to see some hints of larger scale trends in disk structure. So this kind of prompts us to look to more larger samples, possibly to try and understand how debris disks vary with different spectral types. And we're now getting an increased number of CO detections, so we're starting to open this whole window of looking at gas in debris disks. And then finally, we need to have a better understanding of stellar emission. And I'll take any questions.
Meredith, when teaching the words. Questions?
At least based on what we see, you are also expected to see water.
Yes, you would expect to see other molecules. Water is most of the water transitions, if I am remembering correctly, are more in the infrared because the atmosphere. So ALMA is not actually the best telescope for this. This is one of the science cases for the Origin Space Telescope, is to actually look for water lines in protoplanetary, mostly protoplanetary disks because they just have much more gas in them, so it's easier to detect other species. There have been a number of ALMA proposals put in to look for other molecular species in debris disks, CN, and other isotopologues of CO. Alicia and I put in another proposal this cycle to do that for 32297 to try and look for the other CO isotopologues, to try and learn more about the excitation temperature. So it's being done. It hasn't been detected yet. Yeah. I don't actually know where the CO2 is. I don't think, I suspect it's not in the ALMA bands, but.
I've got two questions. First, how do you distinguish CO gas from CO ice? Is it a rotational? You know it's gas and not ice.
Oh, it is these are the like row vibrational transitions in the ALMA bands. You can, in protoplanetary disks, people actually try and you can see the freeze out of all these molecules because you can actually see that the radii of the disk change depending upon what molecule you're looking at. So you can actually probe where in the disk these different molecules are freezing out. That is not something that has been done in debris disks. Yes, so according to the news, we have single-handedly murdered an alien civilization. It's complicated. There are a few things at play. One, right, Proxima is at 0.05 AU. We're at 1 AU. So you can imagine that if you have a flare that's 10 times more flux, whapping something that's now much closer to the star, it could have a much larger impact. And there have been a number of atmospheric models that kind of show that you could actually strip away an atmosphere. So there was another paper that came out using the EVRY-scope, which is a new optical telescope that's doing all sky surveys. And they detected a massive flare of similar size in the optical wavelengths. And they did some modeling of what that flare would do to the atmosphere of Proxima Centauri. And they essentially predict that given the flare rates that we think we know of this star, you would sort of strip away the atmosphere completely within 1,000 years or something. But there's some slight caveats to that in that what is actually most impactful to the Earth's atmosphere is coronal mass ejections. So on the sun, you can classify flares. Flares that are this big are what we call an X-class flare. And on the sun, basically all X-class flares are accompanied by a coronal mass ejection, which is not only radiation, but now charged particles. And the charged particles are what can actually penetrate the atmosphere and do some damage. And we don't actually know whether on M-dwarfs they are also accompanied by coronal mass ejections. That's kind of an open question that a number of groups are trying to detect for the first time a coronal mass ejection from an M-dwarf star. If they are accompanied by CMEs, then that's an extra hit on the habitability of planets like this. But the few X-class flares in the sun that don't have CMEs are in regions of particularly high magnetic field. So it's been hypothesized that having really strong magnetic fields can actually trap the CME, and so avoid having it actually be emitted. And M dwarfs have very high magnetic fields. So you could imagine that maybe M dwarfs don't have CMEs because somehow their magnetic fields are so strong that they just prevent you from having them. So unclear. Did not murder the aliens, even though many news sources that I did.
Okay, well, happily for us, Meredith will be around for a few more years. And
Alan has a question.
Oh,